pretty much it for housekeeping. So let me introduce our speaker today. Today we have Dr. Heidi Newberg. She's a professor in the Physics and Astronomy Department at RPI. Her research focuses on understanding this cool ripple structure throughout the Milky Way galaxy and creating 3D models of stellar streams near the galaxy with her Milky Way at Home project. She's been president of the Dudley Observatory for how many years now? I didn't look up how many years.
I don't know, a decade maybe, I don't know.
A long time. She's been doing fantastic work with the Dudley, so we really thank her for that. And today she's going to talk to us about building big telescopes in space. So take it away.
Okay, I'm glad to be here with you guys. Let me see if I can do this again. Here we go. I don't think that worked.
That did not.
So let me try again. I will go to this one. Now can you see it?
Yes, not in presentation mode, but now we go. There, okay, we got it.
There? Okay. So I want to tell you about something that has not been my regular. So for the past 20 years, I've been doing research just in the Milky Way galaxy. And so that's my, the thing that I'm really an expert at. But I want to tell you a fun story about a new, really exciting, crazy project that I'm working on, where we're trying to build giant telescopes in space. And so I'm going to tell you about the project, how I got involved in it, what we're trying to do, why that's important. And because I am a physics professor, I'm going to have to teach you physics along the way. But there aren't going to be any tests, so you don't have to worry about it. So I'm going to just explain to you what it is we're trying to do and why we're doing it and what it's going to be good for. So telescopes are, of course, you guys all know because you go out to the Octagon barn, right? They're how astronomers learn about the universe. So we detect light from one of my colleagues said, faint, shiny objects in space. And the size of the telescope is determined by its diameter, and that's going to tell you how much light is collected. And because these things are so faint, we want to get the most light possible. All right, so we want to get the biggest telescope there are that we can get, and the largest telescopes in the world are like 10 meters, like 30-something feet in diameter, and there are plans, they don't exist yet, to put like 25 to 40 meter telescopes out there. I just want to kind of start with that. Now, here's some physics. So we detect light. Light for a physicist is an electromagnetic spectrum. Light is an electric field and a magnetic field oscillating through space. And the important thing about this, that the first thing you would ask about a telescope is its diameter, and the first thing you'd ask about a light wave is what's its repeat length. How long is it before it repeats that same electric and magnetic field? And I like this diagram because it shows you all the different wavelengths of light that you can have up on the top. So here you got all the different wavelengths of light you can have, and this is in meters. And then it shows you all the different names that you can have for the different types of light: radio, microwave, infrared. And the only part of this entire electromagnetic spectrum that we can see is the visible. So just this very small part right in here, but you can have any length of light. And I like remember radio waves because my grandfather had a 2-meter radio in his car. So it communicated with 2-meter waves. And microwaves, are about the size of your microwave. And then the X-rays are the really short ones. So you see that there's all these different. Infrared is a little longer than the visible one. So I want to talk a little bit about all the different wavelengths you can see. And now I have this picture. And this picture has at the bottom of it, it has the ocean. And then you can see some mountains behind the ocean. And then the tallest mountains in the world are shown behind that. And then we see on the left is long electromagnetic waves, on the right short electromagnetic waves. And what this diagram tells you is how far down through the atmosphere the light goes. So if you look on the left side, you see in the radio, the light comes all the way down, not quite to sea level, but to some low hills. And the only place where it comes all the way down to sea level is here in the visible. So that makes it extremely convenient that we can see in the visible, because that's the only wavelengths of light from the sun that come all the way down to us. I don't think that is a coincidence. But then you'll see that there are all these other wavelengths, microwaves, infrared, where it comes down, but you'd have to get up an airplane, maybe you could see these, and X-rays don't come down at all. So if you want to see any of these wavelengths that are not the visible ones or the radio ones, you have to go into space. So this is a picture of the Chandra X-ray Observatory. It's I'm always going to tell you the diameter, because that's the most important thing about the telescope. So it's 1.2 meters in diameter, and it weighs like 6 tons. And that's important because it's kind of hard to get 6 tons to leave the Earth and then, you know, fly up there in space. And so, you know, this one was put up on the space shuttle, which was that was a hefty hauling machine, which put stuff up there, but we of course don't have that anymore. And you can see on the right the picture of the telescope being transported in the space shuttle up through space. But I don't think they really launched with it sticking out, but it was pretty that way. So I got that picture. But that's not the only reason that you want to put a telescope in space. There are other reasons you might want to put a telescope in space. Another one is that the atmosphere of the Earth, and we have a picture here of a star that's outside the atmosphere. Here's the star, and then the light is coming down through the atmosphere, and here's a bunch of the atmosphere that has, you know, one temperature, and then there's another temperature and another temperature, and it's moving. And so the light from the star bounces around back and forth, and it will produce a wider thing. So if you have very high resolution, if you don't have much stirring in the atmosphere, you get the top left picture where you see nice sharp stars. And if you see a lot of blurring in the atmosphere, you get this bad seeing one. And you can see if you have 2 objects, and it gets to be very bad seeing as you go towards the right side of this picture, then you can't even see whether there are 2 objects anymore. And so you would like to be able to resolve and have very sharp pictures. And if you need very sharp pictures to resolve things that are very, very close together in the sky, that's another reason you want to put a telescope in space. But the atmosphere is not the only reason that light gets spread out. If you have a telescope and the telescope in space, there's an optical phenomenon that the sharpest picture that you can take with a telescope depends on the diameter of the telescope and that repeat length of the electromagnetic wave. And so the smaller the wavelength, the sharper the picture you can get, and the bigger the telescope you have, the sharper the image you can get. And there's something we call the Rayleigh criterion. It says that if you have the two peaks, here's one peak and another from an object that's next to it, if they're not overlapping each other, then you can tell them apart. If they're just barely starting to overlap, as they are in this picture, then you can just barely tell them apart. But if they are overlapping each other, as they are on the right, then you can't tell them apart anymore. And so that tells you how sharp your picture is how wide those the patterns are from the starlight that comes in. And if you have very long wavelengths, like those meter-long radio waves, you have to have a really big telescope diameter in order to be able to make a good resolution picture. And so in this radio wave is like 1 kilometer across, and in these radio waves, you need 1 kilometer across to get a resolution of 1/10 of a degree, which is not that high in astronomy. And they didn't have enough metal and money to make one big monolithic telescope that was 1 kilometer across. And so they made a lot of little ones, and then they kind of combine the light in a way that you can get to that, what we call diffraction limit of a meter. So big, long wavelengths, you need a really big telescope. But if you're looking at light, this is the telescope that's up on the roof of the Science Center at RPI, a 16-inch telescope that you look through. So this one is invisible light, so like maybe 500 nanometers goes through it. You can get a resolution. The diffraction limit of this is like 1/3 of an arc second. So like, 8 times 10 to the minus 5 degrees, a very, very small amount compared to the 10th degree for that radio telescope. But if you wanted to be able to see things with 1/3 of an arc second, you would have to transport this telescope to space, because on the roof of the Science Center at about sea level, the atmosphere blurs the stars out on the best day to about 4 arc seconds. So you never see the limit from the size of the telescope when you're looking in the optical ones. You have like telescope, but you would never see that limit. But when you go into space, when you're trying to get very high resolution, then that really becomes a thing. You need to get something really big in space. That's what I'm saying, big telescopes in space. All right, so let's look at some more telescopes. There's, for example, there's a bunch of telescopes that are in space. This one was trying to measure very, very accurately the positions of stars in space. And it was called the Hipparcos satellite in 1989, half a ton, small thing, 28 centimeters. They put that on an Ariane 4 rocket, just shot it up there so you can get a little thing. But I mean, look at this. I mean, you got a telescope that's going to be in here, and then you've got like jet fuel like here to put it up there. So you got half a ton, you got all that fuel to go up there, and it's a lot of work to get that up there. If you want to send something bigger, well, in this case, the Hubble Space Telescope, 12 tons. In the days when we had the shuttle, you could put a 12-ton thing inside the shuttle and take that up at a cost of like $450 million. And one of the reasons that we don't have the shuttle anymore is it cost $450 million every time that thing went up in the air. And so that was a lot of expense. But one of the things I wanted to show you about these rockets, the rocket that took this Hipparcos up, you could have things up to 3.8 meters in diameter. Or the space shuttle, you could have 4.6 meters in diameter. Or this Gaia satellite, which went up on a Soyuz frigate MT rocket, you could have things 3.35 meters in diameter. So there is a limit, not just in the weight, but in the size. In fact, size is even worse. All these vehicles only had about 4 meters across to stick your payload in there. And if you want to put more weight on that rocket, you have to put more fuel to get that weight up, and then you've got to put even more fuel to get the fuel that you're putting up there up too. So every time you try to put more weight on this rocket, you get more and more and more fuel, and it's already almost all fuel. So that's another big issue for getting stuff up into space. Now I want to show you a telescope that is not, this is vaporware. It doesn't exist yet. It exists in a laboratory, but is not up there in the sky. This is the James Webb Space Telescope. It was supposed to be up there several years ago. It's now supposed to be another year, but every year seems to be another year. Very over budget, unfortunately. This telescope is supposed to be 6.5 meters across. Tremendously big telescope. You'll see on here that it's only 7 tons, which makes it not that much. It means less than the Hubble Space Telescope, but it's like instead of 2.4 meters across, it's 6.5 meters across. So they managed to make it very, very light. Another thing that you'll see about here is that this 6.5 meter telescope would not fit inside the rocket that's going to carry it up there. We had to fold the mirror in order to stick it up there. So 2 problems that we're having trying to get big telescopes up there in space are that you have to fit it inside that rocket, and 2, you have to get enough fuel to get it up there. So you want it to be light and you want it to fold up if you're going to get something bigger than 4 meters up into space. All right. And so we're trying to do that. Now, why would you want to get something bigger than 6.5 meters up into space? And I want to give you an example that is a really exciting example that everyone's very excited about right now. And that is that if you use that equation that I gave you before, it's the only equation in my talk. Use that equation where when you plug in the diameter of the telescope and the wavelength of light of 10 micrometers or 10 microns, you find out that the resolution that you can get, the best resolution you can get from the JWST at 10 microns is 0.4 arc seconds. 0.4 arc seconds, for those of us who look from the ground, seems pretty good because you can't get better than 0.4 arc seconds from the ground. But you can hope that up in space you can do better than that. And if you're trying to resolve an Earth-like planet from a sun-like star, the closest sun-like star is like 12 light years away. And if you had the Earth and the sun be 12 parsecs away, the angular distance between them would be 0.3 arc seconds, which is less than the 0.4 arc seconds. And not only that, but if you looked in visible wavelengths, it would be 10 billion times bright. The sun is 10 billion times brighter than the planet. And so, you've got a big, broad, blob of the sun-like star. And then there's this teeny, weeny little light really close to the center that you can't even resolve from it, even if it was just the same brightness. And it's 10 billion times fainter. And so this seems like you're never going to be able to look at an Earth-like planet around a sun-like star with JWST, even if it is around the closest sun-like star that there is to us. So the first thing that you now all know to ask, because you know all the physics behind this, is why don't you just look with a shorter wavelength so you can get a clearer picture, because then it's more higher resolution. And the answer is because I said before, 10 billion times brighter. If you go to 10 microns, it's only a million times brighter. And that's way better. And how can that be? So in the end, what I'm going to say is to find Earth 2.0, we're going to need really, really big telescopes in space. So how does this work? So you might have learned in high school that if you heat something up, that it starts to emit light, and the hotter it is, the shorter the wavelength light it is. So here we have a picture. Here's a hot peak right over here, and this peak is happening at a very short wavelength compared to a cooler, in this case 3000 degrees Kelvin is cooler, to a cooler black body radiation, cooler object, which has a longer wavelength. And if you go out to the Earth is way over here, peaking out at 10 micrometers, way out over there. Whereas the sun, as we said before, the sun peaks in the visible. This is like a big coincidence, right? The sun peaks in the visible light comes through the atmosphere, we see in the visible. This is really a great thing. It helps us out a lot to be able to see what we're doing, because this just happens to all work out. All right. So if you look at, there's one thing I want to bring up, because everyone gets a little bit confused about this. Because if you remember high school, you might remember, you get red hot and then blue hot is going to be hotter. But next time you go in the shower, I want to make sure you guys remember that in the shower, blue is cold and red is hot. Okay. In fact, like this handle over here, it's so obvious. Whoops! It's so obvious that red is hot and blue is cold. They don't even put hot and cold on there, or H or C or anything. You just know that blue is cold and red is hot. And I just told you that blue is hot and red is cold. So what the heck? What do these physicists don't seem to know anything? Can't even get in the shower if you're a physicist. I don't know what's going on. And the thing to keep in mind is that in our everyday life, we don't mostly see things that are emitting because of this called black body radiation. And we see this temperature light very much. I always tell my class, I gave a question on the test, that says, the wavelength that Professor Newberg radiates at from black body radiation is, A, infrared, B, visible, 3, C, ultraviolet. And I tell them, no, the answer is it's in the infrared because Professor Newberg's not that hot. And you're supposed to laugh. Anyway, we can't see in the infrared. So we don't see the light that's coming off of stuff, except maybe a fire. If you have a fire, it gets to red hot. So we think of red as hot. We think of blue as like water and ice, but that's not the light that's coming off just from this temperature radiation. The blue is from the reflection of the sky off the water. So it has nothing to do, it's nothing to do with the black body radiation. Okay, so that was just a little aside because I have to put the physics in there. I have to put it in. Okay, so if we look at the right panel, what I said before is that the peak of the sun is down here in the visible, whereas the peak of a planet is actually, in the infrared, a micron or 10 microns. And in fact, if you go out to 10 microns wavelength, it's only a million times brighter. The scale of this picture is not to scale, because if I tried to make an Earth down here that was a million or 10 billion times less faint than the sun, you wouldn't see it. So I didn't really get the scale, but you get the idea. You need to go out where you see emission from the Earth to get this to work. All right, so let's go back to, we need to get a really big telescope. How do we get a really big telescope? So this is a picture of the grinding of the mirror of the Hubble Space Telescope. So generically, to make a telescope mirror, you get a big piece of glass, and then you get this grinding tool, and you take the grinding tool and you run it around on the glass, and you try to eat out a piece of the glass to make the mirror be the right shape. And then you illuminize it or put something on it that'll reflect the light. The picture on the right is the mirror blank. They made is the second mirror. They made 2 mirrors for the Hubble Space Telescope in case one failed. Of course, they put one up there that had the wrong figure on it, and they couldn't switch them, so that was not when it was supposed to fail. But anyway, so this is a picture of the other one that was not covered with aluminum and sent up into space. But generically, a mirror is this part down here, and then the surface of it here is the part that's reflecting, and so light will come in, and then it'll go to the focus, which usually is further out the other way. This is a very deep mirror, just so I could draw it on this slide. So if you have a small mirror that had this particular figure, you'd be able to take this piece out here, and it would not be very thick or very heavy. But if you make the mirror bigger, not only is it just going to be bigger, it's going to be thicker. And anybody who has really bad vision understands this. Their glasses towards the edges just get thicker and thicker and thicker. And if you make these telescopes bigger and bigger and bigger, they get thicker and thicker and thicker. And so they get heavier and heavier and heavier, and they're not going to fold up and get in that telescope into that payload area at all. And so let me erase my scribbling here a minute.
We have a question for you, Heidi, to go back for a second. There's a question from Kathy Moon that says, so we're not observing, quote, light from distant planets, we're observing, quote, heat. That's the question.
Right, so we see that is generated because of the heat. So we're always getting light, but one of the things that's important for astronomy is understanding the physics of light, because we can't go there and take a piece out of it and measure its temperature and do all this stuff. We can't even do experimental science. Experimental science, you have the dependent variable and the independent variable. You change one variable and see how it affects the other one. We can't do that. It's like, here's a star, let's turn up the mass, see what happens. We can't do it. We just have to observe. We're observational, right? We just observe the light that happens to hit us that comes from the space. And then we try to use the light that hits us to interpret what was going on either where the light was generated or what happened on the light's way to us. So we try to understand how matter and light interact. And so what I was saying there is that if you heat up an object, it will emit light, and that's a physical principle. And so the light from, for example, stars is mostly light that comes from that process. If you heat it up and it emits light, there's other things going on, but that's the main thing. I was a little bit cavalier with the Earth because the Earth has two ways that you see an Earth. One is from this temperature, and you would have to look in the infrared to see that temperature light. The other way that emits light is by reflecting light from the sun, which is the way we see here, because we're looking in the visible. But that reflected light from the Earth is just tiny compared to the amount of light from the star, which is why you don't really want to look in the visible. You want to look where it emits in its temperature. Okay, so we're back to looking at this mirror that we're trying to figure out how to make a very big mirror that doesn't weigh much and you can fold up. Where's my pen? I've lost my pen. Here we go. So one way to do this, and this is the way it was done on the Hubble Space Telescope, is you take this part here that's behind the mirror and you dig little holes in it, and you get this, some kind of a structure that has all holes in it, and then strong areas in between the holes that hold the surface in shape, so you can dig it out and make it kind of hollow to make it lighter. Another way that you can do it is by breaking the mirror up into little segments. So you make one mirror that's like this, and then you make another mirror that's like this shape, and then you make another mirror that's like that shape, and then you take all those mirrors and you put them together to make the big mirror. And this is what you see when you see like a hexagonal mirror, like the Keck telescope is one of these, that in order to have all these mirrors fit together and fill space, it's a bunch of hexagons that will do that. And so they make these hexagonally shaped mirrors that are thinner, and then they put them in a shape to make the mirror work. And each one of these individual mirrors has to be ground to a specific shape, which makes it work to make the whole big mirror be the right shape. And so these are much thinner. So these are the mirrors that are supposed to go up with the James Webb telescope. And so they made them very light because they made them out of beryllium, and they made them in this hexagonal pattern and had them all put together to make this very light thing. But as we saw in this picture, that even with this very light thing, we got almost the limit of what we can stick up into space easily in tonnage. And we really are having trouble trying to figure out how to unpack something like that when you get it into space. They're having all kinds of trouble with the sun shield unrolling and everything. A lot of moving parts in space to get a thing all to work. And if you try to imagine making something a lot bigger than that, hard to say how it's all going to get in there. And we want to get much bigger than that. Okay, so now I'm going to tell you a story that a couple of years ago, Tom Ditto walks into my office. Tom Ditto is a long-haired artist who majored in film, and he's wearing sneakers and a t-shirt, an astronomy t-shirt. And he tells me that he's got an idea for how to build a really big telescope that rolls up in space, that will roll out in space. And I'm like, yeah, sure you do. But I talked to him for a while, and then he convinced me he really does know what he's doing. He's kind of an artist inventor type. And I've heard of an artist inventor. This guy, Leonardo da Vinci, was an artist. And he, for example, one thing he did was draw a picture of a helicopter in the late 15th century. But the first helicopter that actually flew and worked wasn't built until the 1940s, which is more than 400 years after the original drawing was made, because there's a lot of little details between that drawing and getting an actual helicopter to get up in the sky. And someone had to believe that this was going to actually work. And so what I've been working on is to try to figure out if this idea that he brought to us of having this, well, I'm going to do it this way, of having this telescope that rolls out in space, it will work. And so, like, suppose you had a 1 meter diameter, telescope over here, and in front of that telescope, you rolled out this like 100-meter long diffraction grating. Then if you had a star that was up in the sky and the light was coming down in this direction, it would collect the light over that whole 1 meter by 100-meter area, and then you could design it so that the light would then be diffracted or be bent and then go into this smaller telescope. So you're collecting up light over a big area and putting that into this small telescope. Okay, so for example, in this case, if you get 10% of the light from the grating to go into the telescope, then you've increased your collecting area by a factor of 10, so you get 10 times as much light into the telescope. But even better than that, the angular resolution, the best, sharpest images that you can get are going to be determined by the longest length in your optical system, so that'd be 100 meters. So you get 100 times smaller stars in there. So instead of being about the Earth being about the width of the sun-like star away from the sunlight star, it's going to be 100 times smaller star, for example. So this would allow us to give very high resolution if we could make such a thing happen in space. And he's got, grandiose ideas and much better drawing tools than Leonardo da Vinci had. He has an idea we can put this on the ground and have this big collecting grating here and have that light go into some telescope-like receivers on the side and do situational awareness, like looking for asteroids or satellites or that kind of thing. You can put this in an airplane and fly it up in the air and get observations that way. You could put it on the moon, or you can fly it in space and get radial velocity of stars. And he's been able to draw all these pictures and imagine how that might be. And he's a very smart, divergent thinking, big thinking kind of person. And those people I've worked with in the past, they always need someone who can then figure out the little details, how that's actually work, what do we actually look at, and how would you put that together? And that's what I'm working on doing. For example, we even could put 2 of these telescopes, one on either side of the grating, and get light that's coming out of the sky and going into this one, and light that's coming out of the sky and going into that one. So maybe we can get twice as much light in the telescope that way. So that's one of the designs we're working on. All right, so how are you going to make a diffraction grating that rolls out in space? It turns out, just coincidentally, Corning Glass here in New York has developed something called willow glass. And willow glass, as you can see here, you can just bend it. And in fact, they wanted to make willow glass so that they could roll it up on this big roll of glass here, so you could get really long pieces of glass and send them to people, because you can't mail 100-meter pieces of glass. But if it would roll up, then you could mail it. So they weren't thinking about the didoscope. They were thinking about other applications. But you could imagine if they making this glass by rolling it over this roller here and then rolling it under that roller here. What if you put a bunch of grooves on this roller, or actually ridges on the roller, which cut grooves into this glass? Then you'd have to do this. We were starting to talk to some people who do this do gratings for a living, whether they could make one of these drums for us. And I think it's possible to make, you have to very, very accurately put these ridges on there to make the grooves in the glass. And then you would have this grating that you could then unroll. So for example, here's a structure you would have in space, and then you have this roll, and I've got these little robots here that are going to unroll this grating out across the struts in space. And so then you can put it inside the cargo bay and send it up there and unroll it and have something that's 100 meters long. So we think that using this technology, it might be possible to separate an Earth-like planet from a sun-like star out to like 30 light years, or for those of you who are astronomers, out to about 10 parsecs, which would be a very interesting thing to be able to do. In order to do that, we would need something like 100-meter long grating. It's all cooled, not going to be heated up by the sun or anything, and maybe 7 meters wide. And it would have to be putting the light into something the size of the James Webb telescope. So that would have to be folded up and stuck up there, but they're figuring out how to do that. And so we think we could do that using a didoscope to find Earth 2.0, which is like one of the holy grails for astronomy right now. We'd like to be able to test some of this technology in space, because starting from, you know, our drawings to immediately put something on a spacecraft is a big step. We're looking at ways to maybe try to do something on the ground. One thing we're looking at now is whether you can find near-Earth asteroids with it, because it's another big thing that people are trying to, you know, to find these asteroids before they hit us in time to deflect them or get ready or do something, so that so that we don't become extinct like the dinosaurs did. It's on the ground, it's a different story, because this whole thing of being able to get higher resolution, you can't do on the ground because you're limited by the atmospheres. You're never going to get higher resolution images from this kind of technology on the ground. We're trying to use another feature of it, which is that you get that light from all different directions in the sky is going to be diffracted into the telescope. So you get light from, you know, maybe 40 degrees away from each other. So you can scan potentially a 45-degree wide swatch of the sky, which would be great for things that are moving or like these asteroids, because you can scan the sky each night with a big area each time and try to look for them. And we haven't really, there's a lot of complication for this ground-based version that we're trying to work out, but we're working on a possibility to maybe try to make something like that happen. And this is kind of a picture of it, that we would have this big grating, and we haven't got the scale for what the grating should be yet, so I don't know what the scale of this picture is, but you're imagining light coming down from this area of the sky and light from that area of the sky, and the red light over here is going to go into that telescope, and the red light that comes down over here would go into this telescope, and the blue light from here goes into the left telescope, and the blue light from the right goes into the right telescope. So it's a complicated design, but we're trying to make a design that for potentially putting something on the ground. But it's a different kind of structure, and we did talk to a vendor who actually, I think, could, for a very steep price, but I think that you could actually just call them up and order this grating. We'd have to assemble it in pieces and it won't roll out, but you can order right now, I think, a grating that would work for that. So anyway, we're thinking about whether that would be a possibility. But I just want to leave you with this picture and this idea that we might be looking at a new way to put a telescope together that would allow us to find Earth 2.0. So that's where I want to end, and I will take whatever questions you guys have about this.
Yeah, I don't understand. I mean, what I know about diffraction gratings is that they separate light like a prism, and so maybe I'm not understanding the difference between that kind of diffraction grating and this kind of diffraction grating.
It's the same diffraction grating, and so to be honest, I thought about trying to teach you that physics in here, but honestly, it took me about a year to get it. What are you talking about? Because I learned about diffraction gratings the same way you learned about diffraction gratings, that it separates light out from a prism, which is exactly what this is doing. What you learned about is if you have a grating like this with two slits and you illuminate it, whoops, these are all supposed to be parallel and perpendicular lines of light coming in, and you've got a screen over here that you're going to get, a central maximum here, where the light from one slit and the other slit come together with coherently. Then, so you end up with a big amount of light here, and then a valley, and another first order diffraction pattern, and then a second order diffraction pattern here. And within the first order diffraction pattern, because the light of a different wavelength will construct at a different place, you'll see that first order diffraction and all of the diffraction patterns beyond this central one will be spread out into a rainbow. Okay. So what we're trying to do is exactly that you have. Let me change my color here. So, ooh, whoops, that wasn't what I wanted to do. Where was I? I changed my color to like red or any other color, whatever my mouse can do. Okay, so so this case we have the light. Let's look at the first order diffraction pattern. It comes in this way and ends up going in that direction to get to the edge of the first order diffraction pattern. If you had a different wavelength of light, it would come in the same way and it would go to a different angle. So we have this set up so that this is a very narrow diffraction pattern, and this diffraction grating is set up so that when you come in at like 0 degrees, the first order diffraction is in this direction. Okay. And what they don't usually teach you in your introductory physics classes is, oops, I don't know what that is. Try erasing this. They don't usually teach you in your first level classes is that if you instead at an angle, then your first order diffraction pattern will be further over. Okay. And so in this case over here, if you come in from this direction, it will be I can't control this too well, sorry. Let me erase that. Actually, let me just see if I can. Oh, erase this. Not that to go away. If you come in at an angle, you're going to get a different color light that will go over here and hit the mirror, which I just missed. Sorry, but so it kind of shows you on the picture, if I can put it back to the original picture, that the light that comes in from minus 30 degrees is red light will end up being in the telescope. The light that comes in from 0 degrees, green light, will go into the telescope. The light that comes in from 15 degrees will be blue light. And so that you see that you get the different directions in the sky will go into the same angle, but the light from each direction in the sky will be a different color at that angle, and the other colors will miss the telescope. Does that make some sense?
I almost get it.
Well, it really takes a long time of playing with it to really kind of get it. And I didn't really get it until we made this scale model where we had a grating that is, I've got an eraser here. We have a grating here on the optical bench. And then we illuminated it with some flashlights and lasers and things. We illuminated the grating, and then the light would go through this mirror and then be focused. I have a good mouse here. It'll be focused in this region and then go into the spectrograph. And now I've got written crazy stuff all over this picture. But if I should try once again, to make it a little easier. It really is a lot easier with a pen and a blackboard. So light would come like down from here, it would hit this grating, it would be diffracted in that direction, hit this mirror, it goes in a straight line, of course, and then it goes back over and hits this spectrograph over there.
Huh.
And we could move these lasers and flashlights into different directions. We can move them along the rail and have them point different directions and make sure that everything kind of works. So because I got to play with it, I understand it, but that's basically how it works.
I'm getting close, but not close. Thank you.
You've got some compliments in the chat box, Heidi, as well as a question from Kathy that says, back at the beginning, how does UV light cause sunburn if it doesn't reach the surface?
You get some UV light that comes through. So yeah, not through the glass, but through the atmosphere, you do get some UV light. Let me see.
Heidi, I have a question. This is Matthew from you all.
Yeah.
I was wondering, can you speak about the prospects of possibly determining the compositions of exoplanet atmospheres with telescopes in the near future?
In the near future? Or with this telescope? This telescope I wouldn't call the near future. You know, so that's like what everyone wants to be able to do, right? To not only image one of these things, but look at the wavelength distribution of light from the exoplanet. In fact, in order to try to figure out what elements are in the atmosphere, because we figure any kind of interesting life must be breathing oxygen, so we're looking for that and other things like that. And you know, if you're going to spread the light out into a bunch of different wavelengths, that makes it even fainter. So all these problems I was talking about of trying to resolve things get harder and harder and harder. And they're actually, this particular telescope, if we get it to work and actually gets built, you can change the orientation of the telescope so that the star that you're looking at is coming from a different direction. And as I just showed here, in that case, the light would be a different wavelength going into the telescope that you're collecting. And so you can actually change the orientation of this grating and change the wavelength of light that you're going to get from the planet, and actually just take a spectrum of it. Now it's, I figured out how long an exposure time would have to be for each different wavelength you were doing across, and it's, you know, it's going to be pretty challenging, but it seems to me to not be impossible. You know, the spectra that people are getting now are from light from the star passing through the atmosphere, and you're looking for a little absorption from the atmosphere from the star that's behind it. And I'm absolutely astounded that anybody's been able to do this at all. But they claim that they have been able to do it, and they get some pretty low resolution spectra, but they are not from things that are like an Earth around a sun-like star. They're from a very giant planet around a very tiny star. And so we're not really very close to an Earth right now. And I have not seen anybody even come up with, they've got crazy ideas for space telescopes to do planets. I mean, they're talking about making this big humongous sail that's like, that you can move around through space, and moving it like 1,000 kilometers away from the telescope and holding it up in front of where the star would be to try to block the light from the star so they can then look at the planet. And you're going to have this telescope you can move around, and then this big flying coronagraph spot that you're going to stick up there. It's just crazy stuff. You know, so I think this is no crazier than that.
If you had a bunch of telescopes, so the circumference, not circumference, but in the course of a year, the Earth is 180 million miles away from where it was 6 months ago, going around the sun. So if you put a bunch of telescopes way out at these perimeters, at the end, you'd be looking at a star from a different angle. You know, if you had one over here at 93 million miles from the sun and one over here 93 million miles away, and now you're focusing in on a specific star, would that angle, would that difference in angle allow you to differentiate between two objects that were light years away?
No, it would allow you to, so we do have very high resolution. I mean, the Gaia satellite, which is, I think, one of the ones I showed you, the Gaia satellite is flying right now, and is getting extremely accurate positions of stars. And it measures not only the position of the star in the sky, but also the speed that it's moving across our line of sight. And so you can very accurately measure the velocity of a star by that technique, and by getting very accurate positions. If you're, like you said, you're on one side and the other, then you can get an idea of the distance to the object. But none of that, I mean, the velocity could potentially tell you whether it's being wobbled by a planet going around it, but it would never tell you whether, it would never allow you to see the two objects separately. It doesn't help you get, I mean, so going from one side of the sun to the other side of the sun does not increase the resolution of your picture. It will allow you to get a more 3D picture. So you get to the third dimension, but since the planet and the star are at the same distance, I mean, it doesn't do anything for your resolution.
Or the brightness, okay, all right.
Doesn't do anything for the brightness either, yeah.
Any more questions for Dr. Newberg? You've got a lot of good praise in the chat box. I don't know if you can see it, but you should scroll through it. Very good. Okay, well, I don't hear anybody chiming in, so I will thank you again. That was an excellent talk. I'm really excited, and I hope that this gets off the ground literally, and we can actually, you know, build one of these things. It'd be really cool. So just a quick update for next month. We have some changes to the original schedule, but we are hoping that one of the professors from Siena College can do a Brea Observatory tour virtually and operate the telescope. If the skies are clear, we'll get to see it live. Otherwise, we'll get a talk on the history of building that telescope, as well as some of the student projects that they're actively working on. So tune in August for that talk, and I will see you all